Hello everyone and welcome to this session. Thank you for joining me again. My name is Dr. Khalid Al-Anazi, and today I'd like to talk about the design principle of centrifugal pumps. For those of you who would like to have more information on this session, I encourage you to visit chapter 4 of the book entitled Fundamental of Turbomachinery. The author of this book is William Bing, and he has great details about the principles of design for a centrifugal pump. And without further ado, let's talk about the content of today's lesson. So in the beginning, we'll talk about the preliminary procedure for a pump design, and then we'll talk about the performance testing or performance curves of a pump, and then we will talk about the difference between serial and parallel connection of pumps, or how the flow rate. In this content, we will talk about how the flow rate as well as the pressure vary when you vary the configuration of similar or unsimilar pumps. And then we'll talk about the system curve and the concept of system curve and performance curve when we talk about turbomachinery devices like pumps. And then we'll talk about some of the applications associated with centrifugal pumps, and we'll show some examples, real example pertaining to the design procedure of a centrifugal pump. So, if have you, if I were to ask you, can you attempt to design a pump? This question is very important for mechanical engineer. You might encounter it the very first thing in your job interview before they even ask you about your name. They might say, "Hey, what are the procedures followed to design a pump?" So the main purpose of this session is to walk you through the commonly known guidelines for designing a pump. And without further ado, I want you to know that there is no rigorous procedure to design a pump. In most cases, the designing aspect of a pump depends on the information available from the customer as well as the experience of the designer. However, one can try one of the following two things. So, if you have this data, for example, suppose that you have a pump, and for this pump you have the information available. Like for example, if I, for example, here, let me erase this. If I bring like okay, I say that here's the performance curve of the pump, and the performance curve involves the head it gives, involves the output power as well as the shaft power and the efficiency. So these four parameters represent the performance curves. So if I have information available, for example, I know how the head changes with the flow rate that the pump gives, and I know that how the output power changes. So if I do have this information, then I can use the similarity laws. For example, I can use these laws. I can use these equations to predict the performance of a similar pump, or I can actually check whether the new pump can be designed by scaling up or down. So based on the required flow rate, you can determine whether you want to design a bigger or smaller pump. I told you, this is an approach, and you have information of one certain pump, and then you want to design a new pump. But how do you know if you want to design a bigger or smaller pump? So sometimes if the test data of the existence if the existed pump is available, then you can use the similarity law to check whether you want a bigger impeller size, for example here, or if you want bigger higher rotation speed. So this is one approach basically, or the other approach is to take a completely new brand design. So what does this mean? This means you have to follow some basic rules and guidelines, as I will be discussing this with you in the next slides. So you either use the data of an existing pump in order to design a new pump through the usage of similarity laws and the information available of the existing pump, or you take a completely new design approach, like you start with the selection of the impeller, you start with the physical dimensions of the inlet and outlet of the impeller, as well as the volume, the blade. So indeed, this session will be focused on number 2 here. So we will talk about, we will go with number 2 because we have already talked about similarity laws, so there is no need to go over 1 again. But the main purpose is to show you step by step in how to design a pump. Okay, so without further ado, let me illustrate for you the procedure in general. So the procedure in general involves, first of all, you need to select the impeller, and I will talk about what will be like. For example, there are some steps that you have to follow in order to determine what type of pump impeller you want. And the figure here shows you an impeller that is it's called radial flow impeller here. But why it's radial? Because the flow enters here in the mixed direction and leaves in the radial direction. If you were to focus here, you will say that, okay, the axis of rotation is this way, and the flow is leaving radially. Because the flow is leaving radially, we are calling it radial flow impeller. Okay, and this is the typical dimensions. We will be talking about this in detail, but just know that, okay, here's my okay. So for example, here's my shaft diameter, and then on the shaft comes the impeller, right? So, and then here is the hub of the impeller. Okay, but here's the tip, here is the eye, sorry, of the impeller, and then you have the tip. So, and here you have D2 here represent the outlet configuration or the outlet size of the pump. So in order to design a pump, there are some procedure that you need to follow. The first one is selecting the impeller, as I have explained here. The first one is selecting the impeller. Second one is sizing the inlet of the impeller. Third step is to size the outlet, and then we'll talk about the blade profile because it's important. So we are talking about impellers from scratch, so you need to select their type first. Is it a radial flow impeller? Is it a mixed flow impeller? Is it an axial flow impeller? So this comes in here. After that, you choose the dimension, like you determine the appropriate dimensions of your impeller. How much do you want the hub to be? Or how much, I mean, what diameter do you want the hub to have? What diameter you want the eye to have? So things like that. The outlet then talks about, but of course, these are based on some criteria, right? We will talk about this in a second. Diffuser and volume, then you determine the shaft power. So you go step by step until you have all the information that are needed to implement the idea on the real world. So now we'll go over selecting the impeller type. Okay, so what is the very first step to design a pump? The very first step, you will select the impeller, as I told you, but the selection will be based on what? Will be based on the required flow rate, head, and rotating speed, the design point. In other words, you have to know the flow rate, you have to know the head, and you have to know the rotating speed. This is rotating speed, This is the head of the pump that you want to get, and this is for volumetric flow rate. So you have to know all of these three information to be able to select an impeller. You know, because this is how are you so the dimension specific speed here, it's a parameter. This parameter combines the rotation speed of the impeller, the volumetric flow rate here, as well as the head. So it combines these three parameters into one parameter called the specific speed. So this specific speed is very important, and it's the main parameter responsible of determining the appropriate impeller type. So based on the NC here, you will choose your impeller type. For example, if you find of course you know the volumetric flow rate, right? In gallon per minute, or later either in gallon per minute, or what, or liter per second, or etc. So it doesn't matter. But then from the specific speed and the flow rate, you will determine what type of impeller you want, right? Either mixed, axial, Francis. Now in radial, here you see the float is exiting at a 90 degree from the axis of rotation. In mixed, in Francis, it enters at some degree, but then leaves in the radial direction. In the similarly here, of course. But if you have a mixed flow impeller, then it enters in the meridianal component and exit in the same direction. But both of these directions are not radial, not axial, so they are in between radial and axial. So the first step, in other words, is to calculate a specific speed, okay? So this is specific speed. You need to calculate it based on the required three parameters. From the calculated specific speed, you determine the impeller type, and then you of course find the efficiency. Let's say that you have found the impeller speed to be the specific speed to be, for example, 1000 with a flow rate of 200, then your efficiency will be around 65. Okay, so here around 65%. Okay, this is the overall efficiency. And then from there, like at this point you say okay, then the appropriate impeller type will be radial, because of specific speed became around 1000 and your flow rate and things like that. But if the specific speed, for example, is 10,000, then you have to select like propeller or axial flow pump. If it's in between, then the impeller have to be have to be this way, like have to be designed this way. So it depends. Based on the specific speed, you choose the impeller type. Once you choose the impeller type, then you proceed and determine the appropriate physical dimensions of your impeller, like impeller inlet, outlet configuration, plate profile, etc. And I kept this slide to show you, the impeller type selection. Now there are, for example, the specific speed based on the European unit, it is this much. Based on the US unit, it's this much. So the units here are different. In the European style, they use for the rotation speed hertz, but in the US style, they use RPM. And so on and so forth for the flow rate and the head. So these are just you can use some conversion ratios, like I have explained here, to convert between the European and the United States specific speed dimensions. Okay, but I want you to note something. Sometimes if you have, like, for example, say that you have a curve like this, okay, and you knew that your best efficiency point, and I have explained what do best efficiency point mean, but let's assume that this is your best efficiency point. Some people might say, okay, in order to get like, for example, at constant flow rate, because this is constant flow rate and this is head, right? So some might say, At the same flow rate and head, let us increase the RPM. Or let me put it this way actually. So say that you are working at this point. This is the best efficiency, right? And then you are in this range, like for example here you are working at this flow rate and you are working at this head. Okay, it doesn't matter, but for example, we know that the best efficiency point of this particular pump is located here. If you at one point say, okay, I want to increase the RPM and get the same flow rate, I mean increase the RPM just to become closer to the best efficiency point, this will not happen. In other words, assuming that you want this flow rate and you want this head, but you want the pump to operate near the best efficiency point. So increasing the RPM is not good idea to shift the performance curve at this specific flow rate, and specific head. So increasing the RPM for this particular case in order to become closer to the best efficiency point will not work. Okay, as RPM are associated with lower long. Why? Because the higher RPMs are associated with lower long-term mechanical reliability. So, and usually one should target at least 7 to 80% of the best efficiency point. And this is just a consideration or a full picture of the best efficiency point in the pump. But this is our topic is focused on our session today is focused on the pump design procedure and selection and things like that. So we have said that specific speed is used to select the impeller type. Once you have selected the impeller type, comes the inlet configuration. In other words, if you were to look here, actually a side view of a radial flow impeller, you are given the shaft here, D sub SH, and you are given the diameter of the hub, diameter of the eye, as well as the diameter of the tip. So the main point here is to what? Is to get, we want to calculate how much shaft diameter we should have, how much diameter of the hub, how much diameter of the eye. So we need to know the inlet configuration of the pump. So you start with calculating the hydraulic power. Now the hydraulic power can be calculated from the required information. For example, you know the flow rate, you know the pressure, and once you multiply the flow rate by the pressure difference between the suction, assuming that here, for example, assuming that here is the suction side and here is the discharge side. So you take the difference between them, for example, BD minus B sub S times the flow rate. This will give you what? It will give you the hydraulic power, like for example here. Okay. So once you get the hydraulic power, you divide it by the overall efficiency. Now the overall efficiency can be found from this figure, okay? The overall efficiency can be found from this figure. Okay, so you find the overall efficiency. You know this because you have calculated, you should have calculated your specific speed and you know how much flow rate you have. You can get the efficiency right away. For example, if you calculate the specific speed and found it to be 1500, and you know that your flow rate is for example how much, 10,000 gallon per minute, then of course going horizontal in this direction will tell you how much efficiency you should have. Okay, you should go, by the way, I'm not accurate here, you should go horizontally in order to be able to read it. You should go very horizontal. Okay. So this point will give you what? Will give you the flow rate at about 750. You go down, down, So the specific speed 2000, more than 2000 versus a volumetric flow rate of 750 will get you into an overall efficiency of this much. So from the overall efficiency, you calculate the shaft power, and then you proceed to calculate the diameter of the shaft from this relationship, which is function of the torque. Torque, now what is the torque? So torque is this much. Shaft of the power shaft, sorry, by the rotational speed of the shaft, or angular speed of the shaft in radian per second. So from this you can sigma sub s here represent the maximum allowable shear stress, and it is actually function of the torque, radius of the solid shaft, and polar moment of inertia. Okay, polar moment of inertia for solid shaft is this much, and then you calculate the diameter of the shaft. Once you get the diameter of the shaft, you can immediately, if you have for example, let us say that you have a leading edge that is inclined this way, then of course the diameter of the hub will be it will be slightly greater than the diameter of the shaft. So it is it's greater than the diameter of the shaft by this much. But if for example, if you are talking about very pure radial flow, then the diameter of the hub will be equal to the diameter of the shaft, since the inlet to the leading edge will be purely radial, and as well as the outlet. But just to give you some information, in this case, no, the diameter of the hub should be the diameter of the shaft plus this much, and if you are referring to this figure, of course. Okay, so this chart gives you the typical operation of a radial flow pump, I believe. I just want to tell you that if you are in the green region here, that means your pump is in good condition. But as you go toward this area, then you have some, you have bigger problems of temperature rise, minimum flow acceptable, like noisy operation. And even if you go this way, so either in the high flow rate or low flow rate region, the pump will not work in its comfortable conditions. The pump works in comfortable condition at this green region. So usually cavitation possibility is low, thermal stress is not that high, the pump is doing good, but at very low flow rates here in this area, you have the possibility of significant increase in pump's temperature, you have the possibility of separation, you have the possibility of not continuous stable flow. So you've seen it sometimes in pump that the flow rate, even the speed is not changing, but you see that the flow rate is fluctuating. So if you were to plot, in other words, if you were to plot the flow rate, for example, let's assume that you have here you have the flow rate and you have time. If you were to plot the flow rate, you might find it something like this. So this, what is causing this is here. So basically that means the pump is working not close to the best efficiency point, or it could be higher, very high flow rate, or it could be very low flow rate, but we know that it's not working near its best efficiency point. If it's working near its efficiency point, the flow rate should not fluctuate like this. So this represents best efficiency point. Okay, please draw for yourself. It's a little bit hard here to draw. And the red here represent what? Far, like far away from who? Far away from best efficiency point. Okay, best efficiency point. So In general, however, suction area and small leading edge blade angle result in low suction velocity. If you have large suction area, like if the suction duct to the impeller is relatively large, and the leading edge is relatively small, then this will result definitely in less suction velocity and high. Well, if it's resulting in less suction velocity, then this means higher suction pressure, which is good for the net positive suction pressure head required. This is a required. Now remember, net positive suction head. Let me make it a little bit clear here. Let me make it a little bit clear. So the net positive suction head available should be always greater than the net positive suction head required. You must always satisfy this condition. So imagine that you have less net positive suction head required, then of course this is an advantage, but not all the times. So if you have less suction velocity and higher suction pressure, this is good for less net positive suction head required, but it's not good if the if this value is high. It's not good, okay? Because you need to have higher than the net positive suction head available will need to be increased in order to compensate for the larger suction area of the pump's inlet. So but a compromise design usually set the leading edge blade angle at around 17 degree, and one important thing to note here is that the flow coefficient of radial flow impeller must be between 0.25